Far beyond our sun lies a star so intense it burns hotter than a supernova's fire WR142. Its outer layers are being torn away, exposing the raw heart of stellar fury. How can such a star even exist? In this video, we'll explore one of the most extreme objects in the cosmos. If you enjoy these journeys, please like, subscribe and share, and tell us in the comments, would you dare to witness a star burning this bright up close? Thank you for watching. Now let's begin. The star sits within the wide disk of the Milky Way, a spiral system whose starlight blends into a pale band that crosses the night, and its larger setting begins with the structure of this galaxy, seen at a scale where arms of stars, gas and dust curve like long lanes of material moving under gravity. The disk holds an intricate pattern of spiral segments, and one of these the Orion arm weaves between larger neighbours and carries pockets of formation where massive stars assemble in clusters. In this arm the gas is not evenly spread. Great clouds hold cold molecular material, while between them lie warmer atomic regions and diffuse ionized zones, each shaped by radiation and winds from hot stars. Along the line of sight through Cygnus, the disk is thick with stellar fields and obscuring lanes, so the glow is rich mottled and crossed by dark rifts where dust hides background light. Within this galactic canvas, the energy that moves through space is varied. Starlight dominates across visible wavelengths, but infrared emission rises from grains of dust warmed by radiation, and radio lines trace cold clouds marked by carbon monoxide and atomic hydrogen. Ultraviolet light from the hottest stars bathes cavities and ionizes gas over large volumes, making faint envelopes that respond to brightness, changes in the geometry of their sources. In the inner galaxy, the bulge surrounds Sagittarius, a star the compact radio source at the center, but at this distance in the outer disk, the gravitational field of the galaxy acts mainly as a steady background setting, orbital motions for the gas and stars in the arm. The disk is not flat. It ripples and warps slightly at the outskirts, and density waves move through it, collecting gas that then forms stars in associations and clusters. Shock fronts in these waves compress. Clouds, turbulence stirs them, and magnetic fields thread the material, changing how gas collapses and how radiation escapes. The Cygnus sector of the sky intersects a stretch of the Orion arm, especially rich in young, massive populations. Stellar associations like those gathered under the broad designation of Cygnus complexes fill the view with layers at different distances, so projected fields can appear crowded even when the real space between groups is large. In this direction, the great rift dust lanes cut the Milky Way's band, and behind those lanes luminous nebulae shine where ionizing photons strike the edges of clouds and peel off electrons, producing characteristic glow. Supernova remnants also exist in the region, their shells expanding into the interstellar medium and leaving imprints of higher temperature plasma that radiates in X-ray and radio bands. These relics, along with winds from hot stars, help carve superbubbles, low-density cavities bounded by swept-up shells, where radiation travels farther and where the next generation of massive stars emerges into a tenuous environment. The balance between cold clouds, warm diffuse gas, and hot rarefied interiors shifts over time as sources of energy turn on and off. But at any given moment, the view in Cygnus captures all stages from dense cores just beginning to assemble to exposed evolved stars that drive strong flux into their surroundings. On the plane of the galaxy, differential rotation shears large features, yet the local picture remains dominated by clustered birth-shared envelopes of ionized gas and overlapping wind-blown structures. Extinction by dust changes apparent colors and brightness, So measured values must be corrected to reveal intrinsic properties of sources embedded within or behind dark clouds. Scattered light links cloud surfaces to the broader radiation field, and thermal emission from dust grains traces where energy is absorbed and re-released at longer wavelengths. Cosmic rays pervade the disk and contribute a background ionization that influences chemistry in cold regions, while the far ultraviolet field sets the boundary layers of photodissociation zones, thin skins around molecular clouds where molecules break apart and atoms and ions dominate. In this milieu, clusters of massive stars act as engines that maintain high energy densities, ionize large volumes, and set up winds that collide with ambient gas. The pressure inside these ionized cavities often exceeds that of surrounding material, driving flows outward until equilibrium with the external medium is reached, or until shocks form that compress and heat gas into new layers. The architecture of such a neighborhood is not smooth, but clumpy, with filaments and knots that guide how radiation travels and where it escapes. Observers infer distances through a combination of photometry, spectroscopy, and geometry tied to the known layout of the Milky Way, and each line of sight through Cygnus threads, several strata making foreground and background separation a careful task. Despite the complexity, the large-scale context remains stable enough to serve as a frame, a spiral disk viewed nearly edge-on along its plane, a sector dense with young and middle-aged populations, and an arm segment packed with luminous sources whose combined output governs the state of local gas and dust. Within this frame, the specific cluster that hosts the star resides among other young groupings, all of them nested in the arm's web of clouds and cavities. The star fields that encircle the cluster show a gradient from crowded nebulous regions to clearer windows where dust is thinner, and across these windows the background of the outer arm shines through. The radiation field that passes through this part of the arm arises from many hot stars, not one alone. So ionization fronts and heating reach broadly, yet local intensity still falls sharply with distance from the brightest sources and with depth into clouds. Kinematics of gas measured along this sightline reveal multiple velocity components, each tied to a different structure, and together they map a layered medium where high-speed expansions from evolved remnants overlap with slower flows from expanding H2 regions. Turbulence injects random motions across a wide range of scales and magnetic fields, though invisible influence how filaments align and how shock-compressed sheets fragment. Dust grains grow in cold molecular reservoirs and erode in harsh radiation and shocks, so grain size distributions vary across the sector, changing extinction curves and infrared colors. Polycyclic aromatic hydrocarbons, complex carbon-rich molecules, fluoresce under ultraviolet light, adding broad features to the mid-infrared sky and marking the edges of photodissociation regions. The total gas column along this direction is high, and the cumulative extinction ensures that some of the brightest sources in the region present with reddened colors in visible light, while in infrared bands the same sources become prominent. Multi-wavelength maps combine these perspectives to show cavities as dim hollows in dense traces and as bright interiors in emission lines from ionized gas, while shells appear as arcs or partial rings sculpted by wind and shock pressure. Over the arm's rotation timescale, these structures drift, but over the shorter timescales relevant to cluster environments, they act as quasi-static scenery-setting boundaries and channels for radiation and flows. Against this backdrop, a rare evolved and extremely hot star finds itself not in isolation, but embedded in a busy lane of the galaxy, surrounded by fields of unresolved stars, by layers of dust that filter and reprocess light, and by gas whose state reflects the combined work of many massive neighbors. The Milky Way context therefore frames every observation from the brightness at different wavelengths to the shapes of spectral lines shaped by intervening material. It also provides the quiet, continuous pressure and gravitational field that hold the arm together, ensuring that clusters and associations remain in coherent swathes that trace the spiral pattern. This is the outer stage, the broad arena in which the region of Cygnus sits, and in which the cluster's light emerges carrying the signatures that make an unusually hot, chemically processed star recognizable against a complex glowing galaxy. The sightline across Cygnus presents layered star fields that overlap in projection, so the sky shows rich patterns of young clusters, bright ionized hydrogen regions and arcs from older remnants that together describe a sector where massive stars form in groups and shape their surroundings with light and wind. The densest concentrations stand out in wide images as tangled quilts of glowing gas intertwined with dark lanes, while deeper views resolve knots where compact clusters ignite and push on the material around them. Large associations of hot stars, especially those dominated by O and B spectral types, pour ultraviolet radiation into the surrounding medium, creating broad envelopes of ionized gas and carving cavities, where the gas is thinner and warmer. In these envelopes, the boundaries are not sharp but graded with a thin skin where molecules break apart under the far ultraviolet field, and where dust grains warm and re-emit energy at longer wavelengths. Outside, the brightest zones faint, scattering from dust, places a soft sheen on the sky, and traces the geometry of cloud surfaces that face the most intense sources. The starfields are not uniform. They cluster around long-lived nurseries, whose outlines are set by filaments and sheets within giant molecular complexes. In the most active sites, ridges of cold material thread the region like cords, and where filaments cross gravitational wells gather gas until a burst of clustered star formation begins. Embedded clusters emerge first as infrared groups hidden behind visible extinction, then as partially cleared groups whose winds and radiation lift curtains of dust and reveal arcs, pillars and scalloped edges sculpted by pressure gradients. Along the same view there are luminous emission regions known for their wide spans, one resembling the shape of a continent, and another like a bird in profile, whose apparent forms are accidents of perspective produced by the edges of large clouds lit by nearby hot stars. Between these nebulae and away from the brightest associations, star-pore patches appear, where thicker dust lanes sit in the foreground, creating the impression of gaps that slowly give way to dense fields of unresolved stars as the line of sight passes through or around the clouds. The roll of turbulence runs through the scene, velocities vary across small distances, eddies, mix warm and cold phases, and shocks generate thin compressed layers that later fragment into clumps prone to collapse. Magnetic fields thread the gas and alter the alignment of filaments, sometimes guiding flows along preferred directions, and influencing how shells expand from clusters or past explosions. Signs of older activity lie in broad arcs where supernova remnants have pushed through the interstellar medium, leaving shells of hot, thin plasma that radiate at high energies and expand into lower density interiors shaped by earlier winds. The color of the light in visible images skews toward red in many zones, because dust scatters blue light more effectively, but corrected measurements show extremely hot sources whose intrinsic colors are much bluer, and these sources dominate the energy budget that sets the thermal state of nearby gas. In radio maps, carbon monoxide lines trace cold clouds with long filaments, while atomic hydrogen extends farther and wraps around cavities that correspond to the influence of associations. In the infrared, the edges of clouds light up where complex carbon-rich molecules fluoresce, outlining photodissociation boundaries as curved rims and knotty arcs that echo the relief of the underlying density field. On larger angular scales, the Great Rift cuts across the Milky Way band through this constellation, creating dark rivers that hide distant star populations and complicate distance estimates, yet also providing contrast that makes glowing edges and bubble interiors easier to pick out. Deep surveys over the past decades reveal that the most massive associations in this sector gather thousands of hot stars, many in loosely bound groups where subclusters drift within a common envelope of ionized gas. The combined winds from these hot stars carry material outward at high speeds, measured in thousands of kilometers per second, and produce a steady input of momentum that builds pressure-driven shells. Where these shells intersect denser clouds, they slow and compress the gas, triggering narrow pillars that point back toward the brightest sources and producing cavities that look irregular with openings where the pressure finds the easiest escape path. Inside the brightest nebula spans, small, dense evaporating globules pepper the view. These globules retain traces of the original molecular cloud and evaporate under the intense radiation, leaving comet-like shapes whose heads shelter tiny nascent stars. Even in regions that appear calm in visible light, high-energy observations show thin strata of very hot gas filling the interiors of wind-blown bubbles and providing pressure that supports the surrounding shells against collapse. The cumulative effect of clustered star formation establishes a feedback loop. Newly formed hot stars ionize heat and stir the gas that remains, which can either disperse and halt further formation locally, or pile up along shell edges and filaments where subsequent generations ignite. Observations of proper motions and radial velocities in this area show multiple streams along the sightline, indicating that several structures at different distances overlap, so careful disentangling is required to connect each glowing surface or dark lane to a particular association or cloud. The pattern of bright and dark features also shifts slowly over decades, as expanding shells move outward by tiny angular amounts, and as illumination changes where dust clears along specific paths. Against the dense background, starfields of the Milky Way plain, prominent beacons anchor the map. A supergiant that marks the tail of the swan stands near the luminous heart of the region, and far from that bright star, sprawling complexes stretch across several degrees, their light softened by dust and their outlines revealing where the underlying clouds meet radiation fronts. Star counts rise sharply in clear windows, then drop near the thickest lanes, and this patchwork helps trace the three-dimensional placement of clouds relative to the dominant illuminating groups. In places where the gas is thinnest, the glow fades to a faint background, and films of ionized hydrogen extend beyond easily defined edges, while where the gas is denser, bright rims wrap around clumps, and sharp transitions mark the interface between hot, ionized interiors and cold molecular exteriors. Across the region, small clusters with a few dozen massive members sit near larger associations that number in the thousands, and both scales contribute to the energy that maintains broad cavities filled with heated, low-density gas. The surface densities of young stars vary widely, with pockets of high concentration near recent bursts and sparser halos, where older populations disperse, and this gradient is visible as changes in crowding and nebulosity across the field. Some arcs follow the outlines of past explosions, others trace the edges of wind-driven shells, and still others mirror the ridges of the original clouds, so the resulting mesh of curves outlines a history written in pressure and light. In the early phases of cluster emergence, dust absorbs a large fraction of ultraviolet photons and re-radiates in the infrared, but as winds clear channels, ultraviolet light escapes more easily, and the visible glow strengthens, revealing a transition from embedded to exposed star formation. Multi-wavelength composites bring these elements into a single picture, where ionized gas, warm dust, and cold molecular structures occupy distinct zones that interlock like layers of a weathered relief, and the bright points of hot stars sit at the centers or edges of the cavities they help maintain. Measured across the breadth of Cygnus, the arrangement of associations, clusters, and remnants forms an extended tapestry of activity whose features are linked by radiation fields, wind flows, and overlapping shells that interact as they expand and thin with distance. Berkeley 87 shows itself as a tight rise in star counts against the crowded band of the Milky Way, with a compact core wrapped by a looser halo that merges into the surrounding field, and within this structure, the population skews toward hot, massive members whose shared radiation sculpts a common envelope of ionized gas. Extinction along the sightline is uneven, so colors shift toward red by amounts that vary across small angles, and differential reddening complicates the task of placing members on a clean sequence. Yet when corrections are applied, a coherent clusterage appears that tracks a young age measured in only a few million years. The surface density profile falls steeply from the center, suggesting mass segregation, where the most massive stars concentrate inward, while intermediate and lower mass companions spread into the halo, a pattern expected in a youthful group where dynamical interactions already shuffle orbits toward partial energy equipartition. Within the core, luminous O-type and early B-type stars dominate the light, and their combined output drives an overpressured interior, filled with warm, ionized gas that pushes outward until it meets denser material and slows into arcs and edges that conform to the texture of the ambient medium. Near the core, nebular emission glows faintly, even where dust dims the visible band, and in narrowband views the gas outlines cavities and filigreed rims that mark the boundaries between hot interiors and cooler surroundings. Infrared mapping shows bright rims from complex carbon, rich molecules at the surfaces of nearby clouds, while radio observations trace longer fingers of cold gas that skirt the cluster and confirm that Berkeley 87 resides in a layered environment where feedback has carved partial hollows rather than a single symmetric bubble. Kinematics tie many bright blue members together through similar radial velocities, and proper motions separate the drifting cluster from the thick background of field stars, allowing a cleaner census even in fields burdened by high stellar crowding. X-ray emission permeates the core, coming from shocks in strong winds, from magnetic activity in young lower mass stars, and from colliding wind zones in tight massive binaries whose flows crash together at thousands of kilometers per second and heat to temperatures that radiate at high energies. The rare oxygen sequence Wolf-Rayet member sits among these hot neighbors, and though it outshines many stars in certain bands through strong emission lines, its continuum is dimmed by dust, so the cluster context helps anchor its distance and absolute scale through association membership rather than through isolated measurement alone. Spectroscopy across the cluster shows helium and hydrogen lines in absorption for the hotter main sequence stars, and for evolved massive objects, broad wind-formed emission features, while fainter members display metal lines that shift with gravity and temperature in ways that trace their position on a young isochrone. The ratio of bright to intermediate mass stars aligns with the standard initial mass function within uncertainties introduced by incompleteness and reddening, and this ratio points to a formation event that built a populous high-end and a still unseen low-mass cohort buried in the glare and extinction. In the halo pre-main sequence, stars with disks contribute infrared excesses and show variability as accretion and rotation modulate their light, and their distribution suggests that star formation in the parent cloud persisted long enough to leave an age spread of a few million years across the broader association around the cluster. The cluster's internal velocity dispersion remains modest for its size, indicating that while stellar encounters occur, the group has not yet dispersed, and gravitational binding still links the core tightly enough to resist rapid dissolution in the tidal field of the galactic disk. Embedded knots at the periphery host compact groups where dust curtains thin in places, revealing miniature arcs and pillars that point inward toward the cluster's brightest sources, evidence that radiation pressure and photoevaporation are at work on remnant clumps of the natal cloud. High-resolution imaging resolves crowded cores into chains of blue-white points, some paired as close binaries, others blended into triple systems, and the high multiplicity fraction among massive stars implies that many winds collide or modulate one another, enriching the cluster with structured outflows and flickering small-scale features that add texture to the shared envelope. The cluster's light spills into the surrounding medium and maintains a low-density atmosphere of ionized hydrogen that flows gently along pressure gradients toward lower density channels, and at the edges where this flow meets denser gas, thin ionization, fronts sharpen the contrast and produce bright rims that arc around clumps. Mass loss from the massive stars collects into a common reservoir of hot gas, whose pressure supports and smooths the interior, while momentum input continues as a steady wind that maintains expansion against the weight of overlying material. Reddening laws measured across the field show slight spatial changes in how dust grains extinguish blue versus red light, a sign that grain growth and destruction proceed at different rates in regions of strong radiation and in calmer shadows just beyond the immediate reach of the brightest members. Photometric monitoring finds small amplitude variability in many cluster stars, sometimes periodic with rotation, sometimes irregular with accretion and wind changes, and these variations ripple through the cluster's integrated light on short timescales, even as the large-scale structures evolve more slowly. The distribution of hot stars in the core is not symmetric. Strings of bright members trace former filaments of the natal cloud, frozen into the pattern of birth long after the gas that defined those paths has thinned, and this fossil geometry remains legible in the present arrangement of the most luminous objects. Where the cluster's wind meets a denser external stream, a faint bowed arc appears that hints at motion relative to the ambient medium, and thin diffuse emission trails away along the likely path of least resistance, adding a directional cue to the broader scene. The halo holds transitional objects that still carry cooler photospheres and yet show early ultraviolet excesses, and together these stars bridge the population from hot massive core members to a more numerous but fainter ensemble that extends the cluster sequence downward toward lower masses hidden by crowding and dust. Across the face of Berkeley, 87 polarization maps reveal aligned dust grains that mark magnetic fields draped across the region, and the pattern bends around cavities and follows residual filaments indicating that the field participates in guiding flows and supporting thin sheets against immediate collapse. Within the core diffraction, spikes from the brightest stars cross in deep images, and around them faint nebulosity shows subtle striations produced by density ripples in the ionized gas, while small detached knots cast tiny shadows further out where they shield thin beams of light. The shared radiation field of the cluster reaches beyond the nominal boundary and influences cloud surfaces several parsecs away, lifting layers of gas into warm skins and opening channels where photons travel farther, an effect visible in the way distant rims are oriented and lit. Proper motion selections carve out a cleaner member list, and reduce contamination from background giants and foreground dwarfs, tightening the color magnitude diagram and allowing a more precise fit to a single young track. Though differential reddening remains a persistent broadening factor, in narrow fields aimed at the core, the density of massive stars rises steeply, and the spatial closeness of hot objects yields a maze of overlapping ionization fronts and small shocks, each one changing its immediate surroundings by tiny amounts that accumulate into a filigree of arcs and scallops. The cluster viewed in deep infrared spreads further than visible images imply, with chains of fainter members extending into regions of higher extinction and hinting at a past in which star formation proceeded along a longer ridge that has since eroded and thinned. The brightest members leave their signatures not only in direct light, but also in scattered halos and in the thermal glow of heated dust within the interior, and these signatures map where energy is absorbed and re-emitted within the common envelope. Against this concentrated assembly, the rare emission line star stands not apart, but within a web of neighbours whose winds, radiation, and positions set the local conditions through which every photon from the core and every parcel of gas must pass. The interstellar medium around the cluster shows layered phases that meet along wavy boundaries, with cold molecular pockets set back in shadowed recesses, warm atomic sheets stretched across sunlit faces, and broad interiors of ionized hydrogen occupying cavities where the combined radiation from hot members remains strongest. Molecular gas, where hydrogen forms molecules, gathers in filaments, threaded with dust grains that grow icy mantles in the cold, and later lose those mantles near brighter surfaces, so grain composition and size change across short distances and alter how light is absorbed and scattered. The atomic phase lies as a skin around these cold cores warmed to a few hundred degrees Kelvin by far ultraviolet light, and in this skin carbon and oxygen remain mostly neutral or singly ionized, cooling the gas through fine structure lines that carry energy away and balance the heating from starlight. Ionized gas, where hydrogen loses electrons, fills the low-density interior around the cluster and maintains temperatures of several thousand degrees, Kelvin set by equilibrium between photoionization heating and recombination cooling, and within this interior the sound speed is higher, so pressure gradients flatten sharp contrasts and smooth small irregularities into rounded surfaces. Turbulence. The pattern of chaotic motions across many scales stirs all three phases and drives density fluctuations that appear as ridges, knots and scalloped edges, while shocks compress gas into thin sheets that later fragment under their own weight or under ram pressure from passing flows. Magnetic fields pervade the region and align dust grains that spin in the radiation field, so starlight passing through becomes polarized, and maps of that polarization trace arcs that bend around cavities and follow the underlying filaments that carried the original mass flows during cloud assembly. Cosmic rays add a faint persistent ionization in the deeper shadows, setting a floor for chemical reactions that build molecules such as carbon monoxide, while at the illuminated edges the far ultraviolet field breaks molecules apart in thin boundary layers known as photodissociation regions, which glow in infrared bands where complex carbon-rich molecules fluoresce. Density contrasts are large. The embedded cores can reach many thousands of particles per cubic centimetre. The atomic skins fall by orders of magnitude to only a few hundred particles per cubic centimetre, and the ionized interiors thin further to tens of particles per cubic centimetre. Yet pressure stays roughly continuous, because temperature rises as density falls, keeping the phases in rough balance across their shared borders. In narrowband images, the ionized interiors appear as soft plates of emission, while the borders sharpen along bright rims where radiation fronts meet denser gas. Those rims sometimes show finger-like protrusions where photo-evaporation peels back material and leaves pillars that point toward the brightest sources. Kinematics measured from spectral lines reveal multiple streams offset in velocity, some expanding away from the cluster interior, others sliding along the plane of old filaments, and at the points where streams cross thin sheets brighten and show signs of shear that thickens into small eddies downstream. Grain charging changes with the radiation field and modifies how efficiently dust couples to gas, so in the brightest zones the grains repel electrons more strongly and reduce recombination on grain surfaces, slightly altering the ionization balance and the cooling efficiency within the interior. The chemical state varies smoothly from core to face. Deep inside the cores, carbon is mostly in carbon monoxide. Oxygen joins molecular forms such as water ice on grains, and nitrogen binds into simple molecules. But near the surfaces, carbon becomes singly ionized, and oxygen returns to atomic form, while hydrogen shifts from molecules to atoms and then to ions, as the boundary toward the inner cavity is crossed. Thin layers of enhanced emission mark where shocks have recently passed, leaving gas briefly hotter than its surroundings. Those layers cool quickly by line radiation and then blend back into the general medium, but for a time they show crisp edges that can be traced across several arc minutes. The pressure inside the ionized interior exceeds that of the surrounding atomic sheets, so slow expansion continues along channels of least resistance, and where the interior meets a denser wall, a bow-like curve forms that wraps around the obstacle and sheds a faint wake of gas eroded from the surface. Thermal instability. The tendency for gas at certain pressures to split into cold and warm phases under small disturbances operates within the atomic sheets, so tiny overdensities radiate more efficiently, cool and pull in material, while tiny underdensities heat and expand, amplifying the patchwork of clumps and voids that decorate the faces of clouds around the cluster. Farther from the bright core, the radiation field softens, and the ionized interior gives way to a more diffuse mixture of warm atomic gas, with embedded strands of partially ionized material that maintain a faint glow and carry sound waves outward, and the strands sometimes intersect to make ladders of emission that outline standing patterns in the flow. Grain destruction occurs in places where shocks are strong, shattering large grains into smaller fragments that raise the near-ultraviolet extinction and change the slope of reddening across the field. In calmer zones, grain growth resumes as atoms stick to surfaces and create mantles that later release simple molecules into the gas when warmed by a passing front. Observers find that the ratio of scattered to absorbed light changes from face to face as the dust population shifts, so some cloud edges show bright reflection halos, while others appear as sharp dark cuts against the background star field. Ionization fronts, the thin layers where neutral hydrogen becomes ionized, behave like moving surfaces that march slowly into the gas as photons chip away at the edge. Evaporation flows stream off those surfaces at a few kilometers per second and feed the interior with newly ionized material that blends into the general plasma. At cloud tips facing the brightest members, compact globules remain each with a dense head and a tapered tail, and within a small fraction of these globules, faint stars still forming leaf jets that drill narrow channels through the surrounding material and add fine threads of shock-excited emission to the already complicated relief. Large-scale maps reveal that the ionized interior around the cluster is not a perfect sphere but an irregular volume dotted with sub-cavities, each one linked to a source or group of sources, and between those subcavities sit narrow walls where pressures from different directions meet and hold, Along several sight lines, the atomic layer shows split lines that indicate two sheets sliding past one another, and the plane between them hosts thin Kelvin-Helmholtz, billows a wave pattern, born from shear that break into small vortices further downstream. In radio bands, atomic hydrogen outlines the broader envelope as a pale sea with darker troughs, where self-absorption marks cooler, denser streams nested inside the warmer flow, and these streams sometimes align with polarized starlight vectors in a way that shows the magnetic field guiding their paths. The overall scene changes gradually with time as fronts advance by small steps, shells drift outward by tiny angles, and the network of ionized lanes and atomic curtains rebalances in response to pressure changes, leaving arcs that brighten for a while, and then fade as the gas redistributes into nearby hollows. At the cluster's perimeter, where the interior meets more tranquil surroundings, the ionized glow ebbs to a thin film, and beyond that film the warm atomic medium resumes control, and the background star field grows clearer through a veil of dust that still shows a faint polarization imprint from grains aligned along the quietly curving field. Winds from massive stars and the aftermath of past explosions combine to hollow the medium around the cluster into linked cavities, each one bounded by a shell where swept-up gas and dust collect, and together these cavities grow into a superbubble, whose interior holds a rarefied hot mixture that carries energy away from the core sources. A single hot star launches a supersonic flow that leaves the photospheric layers and accelerates outward until it crosses the threshold, where line driving and radiation pressure complete the push. As this flow plows into the surroundings, it creates two shocks, one that slows the wind and one that advances into the ambient gas, and between them lies a contact surface, where the shocked wind meets the shocked interstellar medium. In clusters crowded with hot stars, these individual bubbles merge, where their shells touch the interior pressures equalize, and the thin walls reshape into larger arcs that bound a shared cavity. The ambient gas is not uniform, so the shell advances more quickly along lower density channels, and stalls against denser knots which bend the surface into scallops and pillars that point back toward the driving sources. Within the interior, the shocked wind cools, slowly staying at temperatures of many millions of degrees Kelvin. Thermal conduction and turbulent mixing along the contact surface bleed heat into the swept-up shell, raising the shell's pressure and helping to keep it smooth against small perturbations. The energy supply is not steady in detail because hot stars vary, and binaries create colliding wind zones that pulse as orbits carry flows into and out of alignment. Yet on timescales, longer than these small changes, the energy input behaves like a nearly constant engine that inflates the cavity. Chemical composition in the interior reflects processed material from stellar winds enriched in helium, carbon, and oxygen, mixed with ambient gas that ablates from the inner face of the shell. Interface layers host rapid cooling where metals enhance line radiation, and these layers give rise to faint filaments seen in narrow emission features. Supernova events in the wider association add bursts of mechanical energy and cosmic rays. When a shock from one of these events races across a cavity already cleared by winds, the shock remains fast over larger distances, and the outer shell brightens where the pressure surge drives it forward and momentarily thickens it. Overlapping spheres from successive episodes of energy release intersect to make a network of partial arcs and nested rims that map the history of pressure fronts spreading through the sector. The shells do not act as rigid walls. They leak where a weak spot meets a lower density route, and through those openings hot interior gas vents as a faint, fast stream that escapes into the larger environment. Such vents show as chimneys that carry high-temperature material into corridors between molecular complexes, and along their edges, thin shear layers roll into vortices that seed further mixing. In regions where dust survives within the shells, ultraviolet radiation from the core stars heats. Grained surfaces and the thermal glow marks arcs in the infrared, while optical emission highlights the ionized faces and radio lines from carbon monoxide reveal denser clumps embedded within or just behind the rims. The pressure inside the superbubble supports the shell against collapse under external weight, and as long as energy input continues, the shell expands at a few to several kilometers per second, a speed sufficient to reshape nearby cloud faces, but low compared with the velocities inside the hot interior. Gravity of the cluster and of the surrounding arm does not confine the hot gas strongly at these scales, so the shape of the bubble follows the resistance of the ambient medium rather than a simple spherical pattern, with elongation along the easiest paths and compression where heavy filaments resist motion. Magnetic fields thread the shells and interiors. Where field lines run parallel to a shell surface, they stiffen it against short wavelength ripples, while where lines cross the wall, they guide charges out of the interior and reduce the growth of small-scale instabilities, changing how neatly the edge remains defined. Evaporation from the inner shell face steadily loads the hot interior with cooler material that enters as clouds of mixed temperature. These clouds ablate and leave tails that stretch inward, then dissolve into the general plasma, and the fingerprints of this process show up as faint, soft X-rays, and as ultraviolet lines from ions that trace transitional temperatures. The combined effect of many hot stars working together is to keep the interior density low and the mean free path long, so radiation and particles traverse larger distances before interacting, and in this regime even small differences in energy input or local density create noticeable variations in the brightness and thickness of the shell when mapped over wide angles. The kinematics of the shells reveal age relationships among nested arcs, with younger inner rims expanding more quickly and older outer rims coasting more slowly into the ambient medium until drag and cooling bring them toward rest, relative to their surroundings. At locations where the shell meets a pre-existing wall of dense gas, the front compresses. The wall triggers thin sheets of star formation along the contact and then flows around the obstacle, leaving a curved shadow downstream in the hot interior. In places where winds from two bright sources face one another, a thin high-pressure slab forms along the midplane, corrugates under small temperature or density imbalances, and sheds knots that drift toward the nearest pressure minimum inside the cavity. The interior is not empty. It is filled with a sea of ions and electrons at high temperature and low density, sprinkled with patches of mixed gas from the walls, and with internal shocks where winds from close binaries collide. This sea transmits pressure signals, rapidly equalizing small differences across large angles and smoothing out irregularities that would otherwise puncture the shell. The shell itself remains a compound structure with an ionized skin facing the core, a denser atomic layer behind it, and embedded clumps that are leftovers of the pre-existing cloud. Within those clumps, dust protects molecules that persist for a time, before photoevaporation whittles them down to comet-like heads with fading tails. Where the cavity ceiling intersects the larger scale flow of the arm, the superbubble can open into a wider channel and allow interior gas to escape into a neighboring void, thinning the shell and dimming its glow in that direction, while on the opposite side the wall may thicken and brighten where it presses into a denser lane. Over time, as energy sources age, the balance among wind power, radiation pressure, and lingering shell inertia shifts by small amounts that slowly modify the outline of the cavity, yet the overall character of an excavated low-density interior and a bright clumpy rim remains. Observationally, the superbubble reveals itself through a suite of tracers, faint high-energy radiation from the interior plasma optical lines, from the ionized skin, mid-infrared arcs where dust grains irradiate absorbed photons and radio emission, where atomic and molecular gas piles into compressed sheets. Kinematic maps drawn from emission lines show a pattern of near and far side motions that indicate an expanding shell, and the velocity width increases where the line of sight crosses portions of the rim that include both approaching and receding segments. Fine ripples on the shell surface mark where small shocks and photoevaporative flows have worked in tandem to sculpt edges into periodic scallops, and these ripples propagate laterally along the wall with speed set by the sound speed of the denser layer. In the sector that hosts the cluster, the linked cavities and their arcs combine into a common superbubble, and the interior conditions of low density, high temperature and high sound speed extend across the cluster's immediate surroundings as a connected volume shaped by winds and by older shocks that once traversed the arm. Around the star, the immediate surroundings shift from the shared cluster cavity to a more intimate zone where the radiation and wind from a single, extremely hot source dominate the local geometry, and within this zone space presents as unusually clean, with little surviving dust and only faint traces of gas that has not already been overrun by the broader flows from the cluster interior. The continuum field from the star reaches well into the extreme ultraviolet, so small grains that drift near the source absorb energy faster than they can re-radiate and either sublimate or shatter. In grain charging and sputtering events, leaving a deficit of the tiny particles that would normally scatter, blue light, or glow brightly in the mid-infrared. What dust remains sits farther away along local density ridges and lights up only weakly as thin crescent rims whose brightness drops quickly with distance from the star, and maps at longer wavelengths show that these rims are irregular, and interrupted a sign that the medium is clumpy rather than a smooth shell. The gas density immediately surrounding the star stays low compared with the denser walls of the cluster cavity, so any local ionized region driven solely by this source blends into the larger ionized interior and boundary surfaces sharpen, only where the radiation field encounters pockets of higher density. In deep images of narrow emission lines that trace ionized oxygen and carbon, the field shows barely brighter skins on the nearest knots, as if the star is painting thin films on passing clumps, rather than inflating a distinct bubble, and these skins face toward the star and fade along their flanks, a cue to the direction of the most intense illumination. If the star moves through the medium with a measurable speed, relative to the local gas, a bow-shaped feature can appear, where the ram pressure of the incoming flow balances the momentum flux of the wind, but in this case the low density and strong upstream clearing by the cluster keep any standoff distance large, and the surface brightness low, so the arc reduces to a faint broad curve rather than a sharp compact bow. The standoff position for such an arc depends on the square root of the wind momentum output divided by the ambient density, and the square of the relative speed, and for a wind this strong and an ambient density this low. The balance point lies far enough out that the arc blends into the clutter of other rims in the superbubble interior. Along the star's flanks, the radiation field scours small grains from the flow, and leaves gas to carry the charge, and the coupling between dust and gas weakens in this regime, so any streamlines that pass near the source separate into ionized plasma that bends around the star and a depleted dust component that lags or escapes along different trajectories. High-energy photons drive a local ionization parameter that is elevated compared with the immediate surroundings, and in the thin skins on nearby clumps, transitions from singly to doubly and triply ionized oxygen become noticeable, while carbon shows lines from higher ionization, states that require hard photons typical of a very hot continuum. Pressure contrasts across the nearest faces remain mild because the ambient density is low, so evaporation flows off these faces drift at a few kilometers per second into the interior and contribute a thin stream of newly ionized gas that disperses quickly into the general plasma. The search for any compact dust-bright shell around the star yields little beyond the scattered broken arcs already present in the cluster cavity, strengthening the impression that the circumstellar environment contains little solid material that survives close to the source, and that dust is only encountered at the periphery where the cluster's interior meets denser filaments. In the immediate zone, the radiation field also sets grain charging at high positive values, which reduces electron sticking and lowers recombination on grain surfaces, slightly increasing the electron fraction at fixed density and temperature compared with the dust-richer region. The ionized gas around the star remains optically thin in many lines because there is not enough column density to drive self-absorption, so line ratios respond primarily to temperature and ionization state, rather than to radiative transfer complications, making the thin skins on clumps effective probes of the spectral hardness from the source. As the wind leaves the star and crosses into the region where it streams freely, it sweeps past the small clumps and leaves narrow wakes that curl downstream, but those wakes widen and dissipate within short distances, because the surrounding plasma is hot and the sound speed is high, allowing perturbations to spread sideways and erase sharp edges. In scattered light, the field shows only weak halos because the small grains that would provide efficient scattering are missing near the source. Larger grains survive farther away and give a dull reflection along a few rims that are clearly external to the star's personal domain. Polarization maps, when examined at the position of the star, exhibit low degrees of polarization in the inner zone, and a recovery to higher values along the outer arcs, consistent with a grain population that is depleted near the source and more abundant where the medium resumes its standard mixture. The local kinematic pattern also reflects the scarcity of bound gas. Spectral lines toward the star show little to no narrow component at the systemic velocity beyond what is expected from the general interior, and any broadening attributable to a compact circumstellar shell is absent, indicating that the wind transitions from over the stellar layers to the interior without forming a bright, dense shell at small radii in the surrounding medium. Where small, dense knots wander, close, thin ionization fronts bite into their surfaces and leave bright, tiny crescents, and occasionally very short ionized tails point away, as the fronts release gas that streams downstream, yet these microfeatures fade within short projected distances because the tails mix rapidly into the interior flow. In the far ultraviolet resonance lines from highly ionized oxygen and carbon appear in absorption against the star and in very weak emission off to the sides, where the skins on nearby clumps scatter a small fraction of the light, and this geometry adds further weight to a picture in which most circumstellar signal arises in transient encounters with stray density ridges rather than in a lasting local shell. The balance of radiation pressure and gas pressure near the source remains tilted strongly toward radiation, and the resulting force on any dust fragment that does survive pushes it outward swiftly until it meets a denser zone where drag can act, so the distribution of dust is hollowed out near the star and only rises toward the edges where the cluster interior meets the first real walls. Despite the harsh conditions, a few narrow filaments of partially ionized gas cross the field at oblique angles and show gentle bends as they pass, responding to both the general pressure in the interior and the additional push from the star, and the bends sharpen slightly on the upstream side, where ionization changes expand the gas by small amounts. The temperature of the plasma near the source stays comparable to the interior set by heating from photoionization and cooling through recombination and metal lines. Yet the ionization state shifts toward higher stages in a thin angular sector that faces the star most directly, creating a modest anisotropy in the emission pattern from certain ions when viewed in narrowband maps. On scales of small fractions of a parsec, this environment resolves into patches of very low surface brightness threaded by occasional uneven arcs that owe their existence more to chance encounters with clumps than to a symmetric star-centered shell, and the arcs brighten where a lingering shard of denser gas presents a face toward the source. The scene close to the star thus consists of a clean cavity, sparse in dust and modest in gas, speckled with delicate skins on passing knots, and with hints of a broad faint bow that lies far enough away to merge with the composite rims of the cluster's interior. From the star's outer layers a continuous wind rushes outward, and quickly enters a free-streaming regime where collisions among particles remain frequent enough to share momentum locally. Yet the flow as a whole meets little external resistance, so speed rises toward a terminal value of thousands of kilometers per second, set by the balance between gravity and the push of radiation on metal ions. The driver of this wind is line absorption, and scattering in a forest of transitions from oxygen and carbon at high ionization stages, with help from electron scattering that adds a flaw to the coupling between light and matter. Photons transfer momentum to ions, ions share it to the bulk through Coulomb forces, and the result is a steady outward acceleration that begins just above the layers, where the continuum last interacts strongly with radiation. In this acceleration zone, the velocity increases smoothly with radius, and a simple description treats the profile as a curve that climbs from small values near the star to an asymptote far away, while density falls as the inverse square of distance scaled by the local speed. So the inner wind remains denser than the outer, and sets much of the optical depth along radial paths. The gas composition reflects a core that has burned helium into carbon and oxygen, so hydrogen is absent and helium is depleted, and the mean molecular weight is high, which changes the sound speed and the scale height of the flow relative to winds from less processed stars. Ionization stratification appears even within the free-streaming wind because the radiation field hardens inward. Close to the star, higher stages of oxygen dominate, and as the radius increases and density falls, recombination and dilution of the radiation field allow lower stages to appear, making nested shells where different ions contribute most strongly to absorbing and scattering light. Instabilities inherent to line driving seed, small velocity and density fluctuations that steepen into narrow shocks and produce clumps, a phenomenon often called the de-shadowing instability, because small perturbations change how ions see the radiation field and create feedback that amplifies structure. Clumps occupy only a fraction of the volume, leaving a tenuous interclump medium around them, so the wind is not smooth but porous, and this porosity alters how radiation passes through by providing paths of lower optical depth between dense knots. The effective opacity therefore depends on the size and spacing of clumps, as well as on the microscopic cross-sections of the ions. In the densest clumps, the ionization balance shifts by small amounts toward lower stages because recombination proceeds more quickly, and these shifts subtly change which transitions carry most of the radiative force as a function of radius. The temperature of the wind remains high enough to keep heavy ions multiply ionized, set by a mix of adiabatic cooling from expansion heating at small shocks where clumps collide, and photoionization heating from the intense continuum. and the net result is a broad plateau of temperatures of tens of thousands of degrees Kelvin across much of the free-streaming domain. Microturbulent motions accompany the flow and broaden absorption profiles on small scales, increasing the effective line width that the radiation field interacts with, and slightly modifying the efficiency of momentum transfer. These motions arise naturally from the same instabilities that create clumps and from shear between faster and slower streams that run side by side in the accelerating outflow. The momentum carried by the wind equals the product of mass loss rate and terminal speed, and for such a hot source, the momentum flux is large enough that even in the absence of dust, the outward force of photons acting on lines sustains a mass loss that scours deep layers and exposes processed material produced by helium burning, because the wind density declines as distance squares, while speed saturates the outer free-streaming zones become optically thin in many continuum bands, and the radiation escapes while still coupling via discrete lines that remain strong due to population of the relevant ion levels. Farther in, where densities are higher, many lines become saturated along radial paths, and the acceleration relies on photons coming from angles that see lower optical depth. The geometry of the flow is nearly spherical on average, but clumping introduces angular structure at small scales, and rotation can imprint a mild equatorial to polar contrast if present. Yet in this environment, the dominance of radiation pressure and the absence of large dust grains near the source minimize strong equatorial disks or pronounced jets, leaving a broadly symmetric outflow filled with fine texture. Colliding streams within the wind produce soft X-ray photons where local shocks heat patches of gas to several million degrees. Kelvin and those photons are then partly absorbed by cooler wind material, leaving weak emission that escapes through the more porous channels. The presence of this internal high-energy light influences the ionization state by creating additional pathways to higher stages for some ions even at radii where the stellar continuum alone would predict lower ionization. As the wind moves outward, the mass flux stays constant with radius, so any local increase in speed corresponds to a decrease in density and vice versa, and this tight coupling ensures that clumps once formed retain contrast until they are eroded by mixing or spread by the high sound speed of the surrounding gas. The magnetic field, if present at modest strengths, ties to the charged particles and can guide microstructures for short distances, but the kinetic energy density of the flow and the radiative forces dominate the dynamics, so fields likely act more as a tracer than as a controller in most of the free-streaming volume. The opacity sources that matter most for acceleration are metal lines, and their distribution in frequency space determines how efficiently the wind taps the stellar luminosity. In a spectrum crowded with lines, each line interacts with a narrow slice of the continuum, and Doppler shifts from the accelerating gas to saturate and resaturate lines in sequence, allowing many transitions to contribute cumulatively to the push. Because the star's spectrum peaks at high energies, ions that require hard photons remain populated and continue to absorb momentum far from the surface, sustaining acceleration until speeds approach their limit, set by the depth of the gravitational well and by the total available force from the radiation field. The free-streaming wind also carries angular momentum outward, though the amount remains small compared with the star's total budget, unless rotation is very rapid, and the removal of angular momentum through the wind can over long times change the internal distribution of spin. But at the spatial scales of this zone, the main observable effect is the smooth expansion of streamlines away from the star, along lines of sight that intersect the wind close to the star-resonant scattering imprints. Broad absorption troughs at high blue shift in ultraviolet transitions of highly ionized oxygen and carbon, a pattern that maps the velocity law and signals the large terminal speed while emission from the same transitions fills in the red side through scattered photons from other angles. These profiles arise even without a dense outer shell and persist in a wind that remains free streaming out to the distance where it eventually meets the more static medium. The flow's sound speed is much smaller than its bulk speed through most of the domain, so pressure waves cannot easily travel upstream, and information mainly propagates outward, making the wind respond locally to radiation and gravity, rather than to distant conditions ahead. The ionization parameter defined as the photon density relative to the gas density declines with radius as dilution and expansion proceed, yet the presence of clumps with higher density locally lowers it further inside those knots, setting up a mosaic of conditions in which different ions reach their favored stages at slightly different distances from the star, and this mosaic underlies the complex patterns seen in line strengths across the wind. In the free-streaming regime, the wind thus functions as a fast-textured conveyor that transports processed material and momentum outward, maintains high ionization and temperature through a balance of photoionization and shock heating against adiabatic cooling, and presents to observers a set of broad signatures that trace acceleration, density fall-off, and clumping without the need for a bright compressed boundary close to the source. Far from the accelerating layers, yet still within the star's sphere of influence, the free-streaming wind encounters enough external material to slow and heat, and at that radius a termination shock forms that converts ordered bulk motion into thermal energy and creates a hot, rarefied sheath bound on its outer side by a contact surface that presses against the slower ambient plasma of the cluster interior. Inside this interface, the shocked wind reaches temperatures of many millions of degrees, Kelvin set by the square of the incoming speed, and the ions and electrons share energy through collisions over distances that remain short compared with the scale of the layer. So a single high-temperature plasma prevails thin enough to be transparent to much of its own radiation, yet dense enough to radiate faintly in lines and continuum at high energies. The geometry is not a perfect sphere because the external pressure is uneven, and because clumps drift through the region, so the shock bends inward where the ambient pressure is higher, and bows outward where the surroundings offer less resistance, with the contact discontinuity shadowing this pattern at a small offset. At the inner edge of the shocked zone, weak ripples propagate as sound waves launched by patchy wind structure, and where clumps in the wind run into the termination shock, they flatten into knots with internal shocks of their own, raising tiny islands of even hotter gas that cool rapidly and blend back into the surrounding sheath. Conduction and turbulent mixing across the contact surface bleed heat into the cooler external gas, building a transition layer of intermediate temperature, where ions such as triply and quadruply, ionized carbon and oxygen, become abundant, and this layer brightens in ultraviolet lines that trace gas neither as cool as the ambient interior, nor as hot as the freshly shocked wind. Shear at the boundary drives Kelvin-Helmholtz billows that roll into vortices along the surface and peel strips of hot gas into the cooler side while dragging tendrils of cooler plasma inward, and these billows march along the wall at speeds set by the shear and by the local sound speeds on either side, if the external pressure changes slowly with direction. Rayleigh-Taylor-like undulations can also grow where denser cooler layers are accelerated by hotter, lighter gas beneath corrugating the contact and creating avenues where mixing penetrates farther. The tangled result is a multi-phase rind that wraps the shocked wind built from hot cores, warm sheaths and cool threads, each at different densities but in rough pressure balance at a given radius. The thickness of the interface depends on the competition between advection that sweeps material downstream and microphysics that diffuse heat and momentum across the gradient. so in directions of higher wind speed or lower external density, the layer becomes thinner and the shock stands farther out, while in denser directions it thickens and steps inward. Embedded within the ambient interior are small clouds and filaments that wander into the interface. Each one presents a face to the oncoming hot gas and grows a whisker-thin bow shock and a tapered wake where ablated material trails away first as warm, partially ionized gas, and then as hot threads that dissolve into the sheath. These cloud sheath interactions seed further turbulence and modulate the X-ray brightness on fine angular scales, so deep maps would show faint mottling rather than a smooth ring. Non-equilibrium ionization conditions arise in the freshly shocked wind because ionization and recombination lag behind the jump in temperature, and for a time the ionic makeup reflects the pre-shock state more than the local thermal conditions, slowly relaxing toward equilibrium as the gas flows laterally along the sheath. This lag imprints ratios among high-energy lines that indicate how recently a parcel has crossed the shock. Microturbulence inside the sheath broadens emission lines by small amounts, beyond thermal widths, and the superposition of many parcels with slightly different velocities and temperatures creates lines with gentle wings rather than sharp cores, while absorption by overlying cooler gas carves shallow notches where intermediate layers lie along the sightline. The pressure in the sheath balances the ram pressure of the incoming wind on one side and the thermal plus dynamic pressure of the ambient medium on the other. So the termination shock locates itself where these forces match, and modest variability in wind output or in external pressure moves the shock back and forth by small fractions of its radius, gently breathing with the environment. Magnetic fields thread the interface and drape around clouds, guiding charged particles along the surface and suppressing cross-field conduction, which changes the shape of the transition zone by keeping some regions sharper and letting others broaden where field lines run more parallel to the gradient. Where the wind from a nearby hot neighbour flows at an angle into the same sector, the two shocked zones can interact, creating an oblique ridge of higher pressure that kinks the sheath and redirects the lateral flow along the contact, and this ridge acts like a splitter, sending streams towards sectors of lower pressure around the star. Internally, the flow within the shocked wind is subsonic relative to the local sound speed, so pressure signals traverse the sheath and flatten sharp differences left by clump impacts or by local cloud ablation. And this communication helps maintain a nearly uniform pressure despite patchy heating and mixing. Radiative cooling is slow compared with the advection time in the hottest parts of the sheath, so most of the thermal energy remains with the flow as it slides along the contact, yet in the mixed layers where densities are higher and temperatures lower. Cooling accelerates and creates thin, brighter filaments that stand out against the general glow. These filaments mark where ablated cooler gas has reached pressure balance and now radiates efficiently, and they tend to follow the crests of shear waves and the edges of wakes behind clouds that drift through the interface. In the most rarefied directions, the sheath opens into channels where the contact surface skims outward to meet the superbubble interior without much mixing, and along those paths the hot gas vents more freely, and the X-ray surface brightness dips while in directions of higher external density the sheath thickens, mixing strengthens, and the glow increases. The global shape of the termination shock and contact changes slowly as the wind spends its momentum, and as the surrounding interior shifts under the combined pressure of all cluster sources. But on short times, the interface responds mainly to local shear clump impacts and cloud passages, which seed a living pattern of ripples, knots, and threads. Because the star's wind is extremely fast, the post-shock temperature remains high, even where the interface steps inward, so the sheath persists as a high-energy reservoir that communicates pressure to the surroundings and regulates how the free-streaming outflow hands its momentum to the ambient medium. Spectroscopically, the interface shows broad, weak emission in lines from highly ionized oxygen and carbon superposed with narrower components from intermediate layers, and spatially, the brightness peaks at a thin ring or crescent depending on viewing angle and on where clouds and filaments cross the rim. The balance of conduction, turbulent mixing and radiative losses sets a characteristic scale for the thickness of the transition layer, and changes in any one term shift that scale so slight increases in external density, for example, can thicken the layer by boosting mixing and cooling, while slight decreases in wind power can thin it by moving the shock outward into lower density gas where advection dominates. Downstream along the sheath, lateral flows collect into slow rivers that carry mixed gas towards sectors of lower pressure, and where these rivers meet, they create shallow junctions marked by enhanced brightness and by gentle bends in the contact surface, signs that material is being redistributed around the star rather than pushed straight outward. Beyond these details, the essential character of the interface remains that of a thin, hot textured boundary where the wind gives up speed heats and shares momentum with its surroundings through a web of shocks, waves, conduction fronts, and mixing layers that ride over and around clouds and filaments that drift in from the ambient interior. The star's outer atmosphere presents as an expanding, highly ionized envelope, where radiation and motion couple to make broad emission that dominates the spectrum, and in this zone the gas is thin enough for light to escape, yet dense enough for frequent encounters among electrons and ions to set temperatures of many tens of thousands of degrees Kelvin. The material here is not static. It streams outward, carrying with it the imprint of acceleration that began deeper, in so every atom and ion moves through a velocity field that increases with radius, and this motion stretches and shifts the frequencies at which lines absorb and emit. Oxygen and carbon at high ionization stages provide the stronger signatures with triply quadruply and higher ionized states, contributing many transitions that are excited by collisions with energetic electrons and by the absorption and re-emission of the star's intense ultraviolet and extreme ultraviolet light. Because the gas moves rapidly, a parcel of atmosphere sees the stellar continuum at a slightly different frequency than a parcel at different radius, and this separation in frequency space reduces self-shadowing and lets many lines act almost independently, so photons can hand off momentum in a cascade of interactions that both drive the wind and fill the spectrum with wide, smooth features. Within the outer atmosphere, clumps produced by line-driven instabilities travel outward as denser knots inside a more tenuous flow, and these knots alter the local balance of excitation and de-excitation by raising collision rates and by changing the escape probability for photons within a given transition. Where clumps are more common, some lines appear brighter because trapped photons scatter less before escape along porous paths. Where clumps thin out, excitation remains strong, but photons escape more quickly, and the intensity per unit volume falls. The relevant temperatures and densities keep most hydrogen absent in neutral or molecular form, and push helium toward ionization, so metal ions become the principal agents for both momentum and radiative cooling, and their lines act as thermometers and densitometers for the flow. The atmosphere is far from the simple conditions where local thermodynamic equilibrium would hold. Populations of atomic levels are set by a competition among photoionization, radiative recombination, collisional processes and radiative decays all in a moving medium, and the resulting non-equilibrium state produces line ratios that resist a single temperature description. Nonetheless, patterns emerge. Lines from very high ionization stages strengthen closer to the star and fade at larger radii as the radiation field dilutes and recombination proceeds, whereas lines from slightly lower stages grow at larger radii before they too thin into the general outflow. Many transitions show profiles shaped by motion, with emission formed over a wide range of radii and velocities that projects into broad wings, while in some resonance lines a shallow blue-shifted absorption appears, where the wind on the near side intercepts the stellar continuum along the line of sight. The depth of that absorption depends on the column of ions and on the exact overlap between the flow speed and the transition's scattering cross-section. And in this atmosphere, the combination of high speed and strong ionization often yields broad, yet not fully black troughs. In contrast, recombination lines powered by electrons falling into lower energy states after ionization tend to be purely in emission and grow stronger, where densities remain high enough for collisions to populate upper levels and for cascades to proceed efficiently. Electron scattering adds a further smoothing influence by copying light into extended wings around strong features and around the continuum, and this process broadens the tops of the most intense lines into flat or gently rounded crests rather than sharp peaks. The expansion also means that photons emitted in one place see surrounding gas shifted out of exact resonance, so escape becomes easier than in a static atmosphere, and this effect sets the thickness of the layer where a given line can form. Each strong transition then maps to a shell in the outflow, where the combination of density, temperature, and velocity gradient produces just the right conditions for many emissions before escape, so the outer atmosphere reads as a stack of overlapping shells, each one responsible for a family of lines. In the case of such a hot source, oxygen in high stages often dominates the optical and ultraviolet emission, with features tied to 5 times ionized and more highly ionized oxygen, while carbon in triply ionized form adds broad bands that overlap and blend. The line blends create smooth plateaus in some spectral regions, and leave notches or shoulders where neighboring transitions approach, but do not coincide, and the exact shape of these blends offers leverage on the distribution of ions and on the velocity law of the outer atmosphere. Turbulent motions of small amplitude born from local shear and clump collisions broaden lines beyond pure thermal widths, and make the tops rounder still, and small time changes in these motions ripple into tiny variability in line cores that ride on a stable wide base set by the overall wind. The electron temperature in the outer atmosphere is maintained by the balance of photoionization, heating, collisional de-excitation, and adiabatic cooling as the gas expands, so temperatures decline slowly with radius, but remain high enough to keep oxygen and carbon in the ionization stages that feed the most prominent lines over many stellar radii. Because the atmosphere is optically thin in the continuum across much of the outer region, the line-to-continuum contrast remains high, and even modest changes in density or clumping can modulate features by detectable amounts. Polarization across emission features can arise where scattering by free electrons or by asymmetric distributions of clumps rotates the plane of light, and small wavelength-dependent signals reveal the degree of symmetry in the outer atmosphere, and whether the line-forming shells differ from the continuum-forming zone in shape or extent. In directions where the outer atmosphere meets thin skins on external clumps, additional narrow components can appear at small velocities relative to the star superposed on the broad wind-formed emission, and these narrow components fade as the skins drift away or mix. The overall strength of emission responds to the mass loss rate and to the ionization balance set by the stellar luminosity and temperature, so increases in outflow raise densities and collision rates and make recombination lines brighter, while small shifts in ionization can trade strength among pairs of lines from adjacent stages without large changes in total power. In such an extreme source, the high ionization parameter ensures that the outer atmosphere favors lines from ions that require hard photons, so very high energy transitions remain present at radii, where a cooler star would already show lower stages. The outer atmosphere also imprints the ultraviolet and far ultraviolet with interleaved absorption and emission from resonance lines against the hot continuum, and these features measure the wind's reach along the line of sight to the stellar disk, as well as its volume emissivity off to the sides. Time monitoring often finds weak changes in line profiles on scales of days to weeks, consistent with clumps rotating into and out of view, or merging and dispersing as they move outward, while the gross widths and equivalent widths remain stable over longer intervals set by the star's steady energy supply. Across the optical and ultraviolet bands, the resulting spectrum carries a highly processed look, carved into broad humps and valleys by line forests from oxygen and carbon, and smoothed by scattering with the continuum rising from deep layers and the emission from the outer atmosphere layered above it in wide overlapping shells that reflect the structure and motion of gas that continues to stream outward. In a star with such a powerful wind, the idea of a sharp surface gives way to a moving translucent layer, where light last interacts strongly with matter, a pseudo-photosphere that behaves like a shifting skin rather than a fixed boundary, and it appears at the radius where the outward optical depth along a ray falls to about 2/3 for the relevant kind of interaction. Because the atmosphere expands quickly and carries dense clumps embedded in a thinner flow, this layer is not a perfect sphere. It puffs outward where the wind is slightly denser, and retreats inward where porosity gives photons clearer escape paths, so the effective radius depends on direction and on wavelength. At blue and ultraviolet wavelengths where many metal lines crowd the spectrum, opacity rises, and the photosphere proxy sits farther from the star, while in the near-infrared, where line density is lower and free processes dominate the layer, lies deeper closer to the acceleration zone that feeds the wind. The principal opacity sources are electron scattering bound free edges from highly ionized carbon and oxygen and free absorption in the ionized gas. Each process scales differently with density and temperature, so their balance changes with radius and with the local pattern of clumps and interclump plasma. Electron scattering has no strong preference for wavelength, and smears radiation without destroying photons, adding a haze that broadens bright features and reduces the contrast of any limb, while free and bound-free absorption convert radiant energy into heat and push the thermal continuum toward a shape set by the local electron temperature. In such an expanding medium, the radiative transfer does not follow the simple rules of a static layer. Doppler shifts move line resonances out of the way along a photon's path, making escape more likely, and letting the photosphere proxy form in shells whose thickness reflects both the velocity gradient and the microphysics of absorption. Clumping adds a further control knob by creating a porous medium where dense knots take most of the opacity, while gaps allow longer mean-free paths, so the emergent continuum depends not only on the average density, but also on the size, spacing, and optical thickness of the clumps. If clumps are optically thin, the net effect is to increase local emissivity and opacity by boosting collision rates while keeping the scaling with average density predictable. If clumps become optically thick, radiation threads between them, and the effective opacity drops compared with a smooth wind pulling the pseudo-photosphere inward along rays that find the easiest passages. Because the continuum forms over a finite thickness, Limb darkening differs from that of a classical star with a sharp photosphere. Electron scattering tends to flatten intensity across the disk, while expansion and anisotropic opacity introduce gentle center-to-limb variations that depend on wavelength. Spectropolarimetry senses this geometry by detecting small wavelength-dependent rotations in the plane of light, where scattering in an aspherical layer leaves a net polarization. The signal remains small if the flow is nearly spherical in bulk, yet it can rise in narrow spectral windows where line opacity thins and the continuum samples a deeper, more aspherical region. The temperature assigned to the star, called an effective temperature, then becomes a parameter tied to the radius of this photosphere proxy at a chosen optical depth and wavelength regime. Because the layer shifts with wavelength, one must use consistent definitions when comparing models and observations. In practice, the continuum slope across optical and ultraviolet bands, together with the absolute flux corrected for extinction, constrains a combination of luminosity, effective radius, and distance, and models of expanding atmospheres supply the mapping from these observables to a temperature that represents the radiation field at the chosen depth. The high energy of this star pushes the pseudo-photosphere far inward in terms of optical depth, measured in electron scattering alone, yet line blanketing at short wavelengths swells the effective radius in the ultraviolet, and the contrast between these regimes explains why the same source can look slightly larger in one band than in another. Time dependence enters because the wind carries natural fluctuations seeded by line driving. As clumps move outward, paths of lower or higher opacity wander across the face of the star, and the photosphere proxy wobbles by small percentages in radius on timescales comparable to the flow time between the acceleration zone and the main continuum-forming region. These small shifts modulate the brightness at levels that are gentle yet measurable, with careful photometry, and they tweak the detailed shapes of broad emission features that sit atop the continuum. The thermal structure across the layer follows a slow decline, with radius set by adiabatic expansion, photoionization, heating and cooling in metal lines, and because absorption and emission occur throughout a finite depth, the emergent continuum is a weighted sum from warmer inner parts and cooler outer parts, not a single temperature surface. Diagnostic interferometry at long wavelengths can in principle resolve the angular size of the continuum-forming region for the brightest examples and test how the apparent radius changes with wavelength, providing a direct handle on the layering of opacity, although for a source as heavily reddened along its sightline, such measurements require careful calibration and wide baselines. In the inner reaches of the pseudo-photosphere, the continuum couples strongly to the gas through free and bound-free processes, producing a source function close to the local Planck function, while farther out electron scattering adds a non-thermal contribution that lifts the wings of bright spectral humps and smooths the continuum between line blends. Because the layer is defined by an optical depth condition, any change in mass loss rate or in clump statistics shifts its location. A higher mass loss rate thickens the wind and pushes the formation radius outward, lowering the inferred effective temperature for the same luminosity, while a decrease pulls the layer inward and raises the temperature parameter. The dependence on wavelength means that a family of effective radii exists, one for each filter, and that family traces how opacity distributes among electron scattering free and bound-free channels as a function of photon energy. The resulting spectrum carries wide depressions where line forests and edges raise the opacity and push the photosphere proxy outward, and broad windows where opacity falls and the layer sits deeper, giving brighter continua. Embedded within the continuum are shallow imprints from the strongest resonance transitions, not as deep absorption troughs, but as gentle undulations where scattering temporarily deflects photons before escape. The geometry also controls how the continuum illuminates the outer atmosphere and the free-streaming wind. Rays emerging from deeper layers at some wavelengths encounter different ionization and density conditions than rays formed higher up at other wavelengths, imprinting a weak wavelength-dependent anisotropy in the subsequent line emission. In polarized light, the continuum shows a baseline signal set by electron scattering in the photosphere proxy and across certain emission features that form farther out the polarization dips because line photons arise in a thicker, more symmetric volume and dilute the scattered continuum. In sum, the pseudo-photosphere is a living surface defined by optical depth in an accelerating clumped highly ionized wind. It moves slightly with wavelength. With time and with small changes in outflow, it sets the effective radius and temperature used to place the star on a wider luminosity scale, and it supplies the continuum against which the characteristic emission from oxygen and carbon stands out in broad, smooth relief. Beneath the continuum-forming layers, the atmosphere thickens into sub-photospheric zones, where radiation diffuses through matter rather than streams freely, and in these depths the gas carries the imprint of helium burning rich in carbon and oxygen, with traces of neon and heavier ashes, so the mean molecular weight rises, and the balance between pressure from light and pressure from particles tilts toward radiation. Photons make their way outward by repeated scatterings and absorptions, and the path a photon follows is short compared with the size of the layer, so energy transport acts like a slow drift through an opaque medium whose resistance is set by an average over many kinds of interactions. Electron scattering supplies a smooth background that redistributes light without destroying it, while bound-free and free-free processes tied to carbon and oxygen ions convert radiation into heat and back again, and the combined opacity climbs in narrow temperature bands, where ion group elements present a forest of lines, creating a local bump that changes the radial gradient required to carry the luminosity. When opacity rises in such a band, the layer above receives less flux for the same gradient the local radiation pressure builds, and the gas puffs outward until a new balance establishes with a slightly larger scale height. The result is an inflated zone of moderate density perched above denser strata, where the gradient steepens once more. In the hottest subphotospheric depths, the gas behaves nearly fully ionized, so the sound speed depends mainly on temperature and on the high molecular weight, and the pressure profile follows from a balance between gravity pulling inward and radiation plus gas pushing outward, with the outward term close to the level where a small additional opacity would tip the layer toward loss of hydrostatic support. The stratification is stable on average, but it hosts gentle motions because the opacity bump and the high radiative gradient can create thin convective bands where ascending cells carry heat alongside diffusing photons. These cells do not dominate energy transport over large radii, yet they seed turbulence that imprints small fluctuations in density and velocity across the layer. The material is compositionally uniform over the thickness relevant to emergent light, because mixing at these temperatures smooths any residual stratification left by earlier burning stages, so carbon and oxygen fractions remain high, and helium remains low, and hydrogen is effectively absent. With few bound electrons per unit mass compared with a hydrogen-rich mixture, the distribution of opacity among processes changes, elevating the relative importance of metal lines and edges, and shaping how the radiation chooses pathways through the gas. The temperature declines outward from values deep enough to keep iron group ions in intermediate charge, states that present many lines to the radiation field to cooler values above the bump where those ions shift stage and the forest thins, and each shift modifies the slope of the temperature gradient required by diffusion. The density likewise falls steeply, with radius not as a sudden drop, but as a smooth decrease set by gravity and by the increasing role of radiation pressure, and the product of density and opacity fixes the rate of diffusion so that the flux remains equal to the luminosity carried from deeper within. At a certain radius, the finite outward drift of matter transitions toward outflow as the wind begins to take hold. Below that point, the mean motion is small and subsonic, and the gas stays close to hydrostatic. Above it, the acceleration becomes measurable, and the speed rises toward the sonic value, and the sonic surface marks the true divide where the static star shades into the expanding atmosphere. In the layers just below the sonic point, compressibility effects appear as small departures from simple stratification when local opacity patches share space with low opacity corridors, and radiation threads the corridors more efficiently, leaving a mottled distribution of radiative force that gentle motions attempt to smooth. The thermal coupling of gas and radiation remains tight through these depths, so temperature fluctuations are muted and short-lived, and any local heating by viscous or magnetic dissipation is promptly shared among particles and photons and spread outward by diffusion. Magnetic fields, if present at moderate strengths, contribute little to the pressure budget compared with radiation, yet they can channel convective plumes and help organize thin layers of shear where differential rotation or wave motions transport angular momentum. Such layers are shallow and remain buried beneath the radiative zones that dominate the column. Acoustic waves excited by small convective cells or by microscopic instabilities at the opacity bump travel upward with increasing amplitude as density falls, and many of these waves dissipate before reaching the continuum-forming layers, leaving behind a faint background of heating that slightly reduces the radiative gradient needed for balance. The equation of state in these depths reflects full ionization, with relativistic corrections insignificant at the prevailing temperatures, so the adiabatic index remains close to the value expected for a monatomic gas with radiation pressure included, and the presence of heavy elements primarily affects opacity rather than compressibility. Because the luminosity to mass ratio is large, the ratio of radiation force to gravity approaches unity over finite intervals, and where it lies very close, the layer becomes susceptible to gentle inflation. This inflation is not a global upheaval, but a localized swelling that changes the geometric thickness of the sub-photospheric envelope by a small fraction and lengthens the diffusion path of light. The microphysics that sets opacity in these conditions is sensitive to the exact distribution of ion stages and to the density, so slight changes in composition or temperature adjust the height and breadth of the ion group bump and thereby shift the depth of the inflated region. Deeper than the bump the opacity falls, radiation escapes less reluctantly, and the required gradient relaxes so the stratification tightens and the density scale height shrinks, drawing the gas into a compact interior that feeds energy outward with less dramatic structure. Within the sub-photospheric envelope, the radiative flux remains nearly constant with radius, because it carries the star's luminosity, but the local energy density falls as temperature drops, and the time a photon takes to escape, when averaged over many scatterings, still remains very short compared with evolutionary times, so the layer tracks the current energy production of the core without large delays. The balance among diffusion convection in narrow zones and wave transport sets the fine structure of the envelope, and this structure imprints on the layers above by determining the position of the sonic surface, the density at that surface, and the seed perturbations that rise into the accelerating flow. Where the opacity bump creates a convective band, the convective Mach number stays well below unity, so flows do not shock. Instead, they exchange momentum with the surrounding radiative medium through drag and excite a spectrum of waves whose wavelengths span from fractions of the local scale height to several times that scale, and these waves interfere and form standing patterns in places where boundary conditions favor resonances. Rotation modifies the shape of equipotential surfaces and splits gravity into a radial and a small latitudinal component, making the effective gravity slightly lower at the equator than at the poles. The radiative flux then distributes accordingly marginally brighter, where gravity is higher and the sub-photospheric temperature and density adjust to maintain diffusion in step with this pattern. Such latitudinal differences stay gentle unless rotation is extreme, and in a star dominated by radiation pressure, the departures from spherical symmetry inside the envelope remain small, yet they suffice to imprint subtle anisotropy on the emerging continuum once it passes through the pseudo-photosphere. The composition also determines the rate at which free electrons are available per unit mass, changing the baseline for electron scattering, and thus the depth in terms of mass at which the optical depth condition defining the continuum emerges. With carbon and oxygen dominant, the electron count per gram differs from a hydrogen-rich case, and this difference moves the layer of last strong interaction inward or outward by small amounts at a given luminosity and mass loss rate, altering the mapping between observed flux and the inferred effective radius. Farther down, where temperatures rise toward values that strip even iron group elements of most bound electrons, the line contribution to opacity weakens. The envelope becomes more transparent to its own radiation per unit mass, and the gradient needed for diffusion reduces, tightening the stratification into a regime that behaves simply and passes energy with fewer local irregularities. The sub-photospheric layers taken together form a cushion of high opacity and high radiation pressure that grades smoothly into the accelerating atmosphere above and into the compact hotter interior below, and their thickness, temperature profile and small-scale motions set the conditions at which the outward drift of gas becomes an outflow, and the diffuse sea of photons becomes the continuum seen against the sky. Temperature falls from the deepest visible layers toward the outer wind in a steep but structured cascade, and the pattern emerges from how radiation trades energy with matter as it diffuses outward through an envelope dominated by carbon and oxygen, and then enters an accelerating flow. In the sub-photospheric regions, the gas and radiation couple tightly, so a small change in opacity forces a compensating change in the local gradient that carries the luminosity, and where the iron group opacity bump raises resistance, the layer puffs, slightly spreads the gradient over a larger thickness, and leaves a shelf in the temperature profile that stands above a hotter interior with a sharper rise below. At these depths, the temperature sits far above 100,000 degrees Kelvin and declines outward at a rate set by diffusion through a mixture where electron scattering supplies a smooth background and metal edges and lines add narrow bands of extra blockage. The diffusion path integrates over frequency and angles and yields a mean opacity that sets the slope of the temperature curve. Approaching the continuum-forming region, the temperature still falls but less rapidly, because expansion begins to share the burden of cooling photons, continue to diffuse, yet parcels of gas also do work as they start to move, turning internal energy into kinetic energy and lowering the local electron temperature without a large change in radiation field. The pseudo-photosphere marks the place where the continuum appearance arises, its temperature converted into an effective value through the mapping of luminosity and radius lies in the range of 200,000 degrees Kelvin for a source of this class and that parameter, summarizes how hot the radiation field must be at the depth, where optical depth reaches the chosen value. Above this layer, the gas enters the accelerating atmosphere, where radiative heating and line cooling balance with adiabatic expansion to make a broad plateau of tens of thousands of degrees, Kelvin high enough to keep oxygen in high ionization stages and to sustain the line emission that dominates the spectrum. The plateau is not perfectly flat where clumps run into one another. Thin shocks heat small patches to higher temperatures, producing soft X-rays that leak into the surroundings and briefly raise local ionization before being absorbed by cooler material that then re-emits at longer wavelengths. Farther out as density falls and the ionization parameter declines, recombination shifts, populations toward lower stages, and cooling becomes more efficient per particle, so the electron temperature eases downward while remaining high, compared with typical H2 regions because the hard radiation field continues to pump energy into metal ions. At the termination shock, the temperature jumps to many millions of degrees Kelvin in proportion to the square of the incoming speed. Their ions and electrons share energy through collisions until a single, hot plasma prevails, and conductive and turbulent mixing with cooler surroundings builds a ladder of intermediate temperatures along the contact layer. Thus, the outermost stratification carries three broad steps: a hot shocked sheath at the highest values, a wind plateau at tens of thousands of degrees Kelvin, and a deeper, much hotter radiative interior that sets the effective temperature where the continuum emerges. Within the interior below the photosphere proxy, the temperature profile follows the requirement that the radiative flux equal the star's luminosity. Where opacity is modest, the gradient can be shallow. Where opacity spikes, the gradient must steepen, and in thin zones a small convective assistance appears when the radiative gradient exceeds the local threshold for overturning. These convective layers are gentle in this environment, and serve mainly to iron out small irregularities in the temperature field, feeding a spectrum of acoustic waves that travel upward and dissipate in less dense layers, adding a faint supplemental heating that subtly flattens the gradient just beneath the continuum-forming zone. Rotation introduces only minor latitudinal differences in effective gravity, so any thermal contrast between poles and equator remains small. The diffusion adjusts to send a slightly larger flux where gravity is higher, and the temperature at a given optical depth sits a little lower where the flux is larger, producing a weak anisotropy that becomes part of the footprint of emergent light. Because the envelope is hydrogen poor and helium depleted, the electron supply per gram differs from a hydrogen-rich atmosphere, and this difference shifts the depth in terms of mass column at which electron scattering becomes the dominant channel, moving the point where the temperature tied to the continuum is set. The measured color temperature across ultraviolet bands can diverge from the effective temperature because line blanketing absorbs and redistributes flux carving dips and windows that mimic cooler or hotter slopes depending on wavelength. Models of expanding line blanketed atmospheres convert those slopes back into a consistent temperature profile, revealing a high inner temperature that supports the classification of the star. In the wind, the thermal balance relies on a competition between photoionization heating line and free cooling and adiabatic expansion. The last term increases with radius, as density drops, so beyond a few tens of stellar radii, the electron temperature sags, even though ionization can remain high in the most exposed directions. And this decoupling of ionization state from local temperature is a natural outcome in a flow bathed in hard radiation. In the mixed transition zone at the wind-ambient interface, conduction across steep gradients supplies heat to cooler filaments and peels them toward intermediate temperatures, where metal line cooling becomes efficient, so the emission peaks there in ultraviolet features that trace gas at a few 100,000 degrees Kelvin, while the hottest interior of the sheath radiates more weakly because its density is low and cooling times are long. Viewed as a function of optical depth rather than radius, the stratification condenses to a rapid change from a deep radiation-dominated temperature of several 100,000 degrees Kelvin at depth of many scattering lengths through a continuum layer where the source function approaches the local Planck function, to an atmosphere where the source function becomes a mix of scattering and thermal emission, and the temperature holds near a wide plateau before tapering down. The rapidity of the change across the continuum-forming region explains the sensitivity of effective temperature to small shifts in mass loss. A slightly denser wind pushes the layer outward to cooler physical radii and lowers the inferred effective temperature, while a slightly thinner wind pulls the layer inward and raises it. Time variability of clumping introduces tiny reversible ripples in the temperature at the optical depth that dominates a given band, and those ripples translate into low-amplitude brightness and color changes on timescales set by the flow time through the continuum region. Spectral line ratios from adjacent ionization stages of oxygen and carbon taken together with recombination continua sample the temperature at different depths and radii and show the expected pattern: higher stages stronger near the photosphere proxy, lower stages strengthening outward, with the boundaries between them shifting slightly as the wind breathes. In polarized light, the temperature stratification reveals itself indirectly through wavelength-dependent scattering depths. At shorter wavelengths, increased opacity moves the continuum layer outward into cooler gas with more electron scattering, raising the polarization baseline slightly, while at longer wavelengths the layer sits deeper, in hotter, denser zones, where true absorption is stronger and polarization falls. Across all these diagnostics, the essential picture holds that temperature declines steeply. From inner radiative depths to the expanding atmosphere flattens into a high plateau, sustained by hard radiation and rapid advection, and then divides into a hot post-shock sheath and cooler mixed filaments where the wind hands energy to the surrounding interior, and each part sets distinct spectral and imaging signatures that trace the thermal ladder from the continuum layers to the edges of the star's influence. At the center, the energy source operates in layers of very high temperature and density, where nuclei collide often enough to build heavier elements, and the chemical pattern observed at the surface guides the picture inside because a wind has peeled away the outer lighter strata and left a core rich in carbon and oxygen. In such a core, the temperature stands at hundreds of millions of degrees. Kelvin, and the density reaches values that bind matter tightly, so reactions proceed through channels that require close encounters among alpha particles and heavy nuclei. During helium burning, 3 alpha particles join in sequence to form carbon in the triple alpha reaction, and at only slightly higher temperature an alpha particle fuses with carbon to make oxygen. Both channels release energy and fill the core with the very atoms that dominate the spectrum in the atmosphere, in models for stripped very massive stars that match the observed composition of an oxygen sequence. Wolf-Rayet star, the core sits near the end of helium burning, or has just begun to burn carbon, and the boundary between these cases remains a point of study, because mass rotation and mass loss each adjust the timing. If carbon burning has started 2 carbon nuclei combined to produce elements such as neon sodium and magnesium with the help of gamma rays that carry away energy, the rate depends strongly on temperature, so small changes in the core conditions alter the pace by large factors. The core does not remain chemically uniform while these processes run. Convection mixes central regions where energy release is high and carries fresh fuel inward while moving ashes outward, and this overturning maintains nearly uniform composition within the convective zone, while sharp gradients form at its edge. Radiation also carries energy, but in the deepest layers photons scatter so frequently that diffusion becomes slow compared with the stirring of convective cells, so convection shoulders most of the transport within the burning core, while radiation takes over across the quiet zones that lie farther out. The high energy density at these temperatures produces pairs of electrons and positrons, and their presence alters the pressure that resists gravity. When pairs form, they absorb energy and reduce the stiffness of the gas, and the core responds by compressing slightly until the reaction rates rise enough to restore balance. Neutrinos carry away a large fraction of energy in these conditions through processes such as pair annihilation and plasma emission. Neutrinos interact very weakly with matter, so they leave the core almost freely and act as a cooling channel that shortens the time a given burning stage lasts. In helium burning, the timescale remains long enough that the core structure adjusts gently, but once carbon burning begins, the timescale contracts and convection must replenish fuel in step with a more rapid reaction flow. The detailed balance among burning mixing and neutrino cooling sets the thickness of the central convective region and the slope of temperature and density just outside it. The equation of state through these depths remains that of a very hot, nearly fully ionized gas plus radiation, with electron degeneracy playing only a limited role compared with cooler compact objects. Yet partial degeneracy can emerge in dense pockets at certain stages and shift the thermal response locally. Rotation introduces mild departures from spherical symmetry and effective gravity, and rotational mixing can shuttle fresh helium or carbon into the active zone, extend the burning lifetime by a small fraction, and smooth chemical gradients effects that depend on the angular momentum profile left after prior mass loss. Waves generated at convective boundaries propagate into adjacent radiative layers and deposit momentum where they dissipate, adding a subtle transport of angular momentum and a small amount of heating that slightly modifies the temperature gradient near the edge of the core. The network of nuclear reactions operates as a chain whose branches depend on temperature and density. In helium burning, the chain is simple and proceeds mainly through triple alpha and alpha capture on carbon, while in carbon burning side branches produce neon and sodium among other nuclei, and each branch seeds the next layer outward as ashes accumulate. Ashes do not remain in the very center alone. Convection spreads them across the core, and as energy moves outward, the surrounding layers adjust their pressure and composition, forming shells where different reactions either await ignition or remain inactive because temperature is too low. The core stays in hydrostatic equilibrium on short timescales, with pressure gradients balancing gravity at every radius, even while composition and temperature evolve, and this quasi-steady balance allows energy to flow outward without sudden structural upheaval at the present stage. Opacity in the inner radiative zones surrounding the core arises from electron scattering and from absorption by highly ionized heavy elements. Because hydrogen is absent and helium is low, electrons per gram are fewer than in a hydrogen-rich mixture, and this shifts the mapping between luminosity and the temperature gradient needed to carry it. The luminosity generated in the core equals the energy required to sustain the observed radiation field and to offset neutrino losses, and the sum passes outward through the sub-photospheric envelope, where diffusion dominates, then through the accelerating layers where radiation pushes the wind. The steep temperature sensitivity of both helium and carbon reactions makes the core self-regulating. If a small compression raises temperature, reaction rates leap upward, energy release increases and expansion follows until temperature drops back toward the level set by balance with cooling and transport. If temperature falls, rates drop and contraction supplies the compensating heat. In the convective core, mixing length motions rise and sink at subsonic speeds, with trajectories limited by stable stratification above and by buoyancy within. These motions keep entropy almost uniform across the region, resulting in a flat temperature profile compared with a much sharper gradient in the surrounding radiative layer. The boundary where convection ends and radiation takes over is not perfectly sharp in 3 dimensions. Overshooting plumes penetrate a small distance into the radiative zone before losing buoyancy, and this overshoot extends the mixed region by a modest fraction of a pressure scale height, an effect that changes the mass of fuel available to the core and alters the duration of the burning stage by a measurable amount. Magnetic fields, if amplified by dynamo action within the convective core, can rearrange angular momentum and resist shear at the boundary, yet their contribution to pressure remains small compared with gas and radiation, and their chief influence lies in transport rather than in direct support. The energy released per unit mass in helium and carbon burning differs by only moderate factors, but the neutrino cooling rate rises steeply with temperature, so as the core warms, the fraction lost to neutrinos grows, and a larger portion of energy bypasses the photons that eventually appear as the observed luminosity. The outward energy flux that does emerge as radiation sets the conditions at the sonic point above, and thus the mass loss rate through its role in driving the wind. The path from core to wind therefore ties nuclear power to outflow indirectly, through layers that translate heat into radiation, and radiation into acceleration. Composition gradients laid down by the core define the menu of ions available to line driving in the upper atmosphere, so the chemistry of the engine influences the efficiency of the wind through the supply of carbon and oxygen ions that absorb momentum from light. At the very center, the nucleosynthesis pathway advances slowly, compared with the turnover time of convection, so the core maintains a near uniform mixture at any given moment, with helium falling and carbon and oxygen rising and helium burning, and with carbon falling and neon and magnesium rising if carbon burning runs. The thermal profile remains smooth, climbing inward toward a maximum set by hydrostatic balance, and the need to supply enough energy to match radiative and neutrino losses. No abrupt temperature spikes occur across the active zone because convection damps them by mixing entropy quickly. The mechanical response to energy generation appears not as large-scale pulsation, but as gentle structural readjustment that slightly modifies radius and density profiles while preserving the overall stratification that allows energy to pass outward and the wind to draw momentum from light. The core energy generation thus acts through sustained nuclear channels in a carbon and oxygen-dominated mixture at very high temperature with convection-moving fuel and ashes, neutrinos siphoning energy directly to space radiation, diffusing through surrounding layers and the combination setting, the outward flux that continues into the sub-photospheric envelope without interruption. Rotation leaves a quiet imprint across the star and its outflow by slightly lowering effective gravity at the equator and by introducing gentle latitude differences in radiative flux, and in such a radiation-dominated envelope, the departures from spherical symmetry remain small, yet they are sufficient to organize structures in the wind that repeat on timescales near the rotation period. The surface layers defined by the moving continuum depth in the accelerating flow carry a spectrum of small inhomogeneities that seed co-rotating interaction regions, extended spiral-like zones, where slightly faster and slightly slower streams meet and share momentum, and these zones travel with the star and modulate the line emission and absorption as they rotate into and out of view. In the outer atmosphere, the co-rotating pattern appears as weak bumps that drift across broad emission profiles and as shallow blue-shifted notches that march through resonance absorption. features whose progression rate offers a handle on the period when geometry and inclination permit a clean readout. Photometry taken over many nights often shows low amplitude, nearly sinusoidal changes, consistent with the surface brightness pattern that turns with the star, while spectropolarimetry records tiny rotations in the plane of light across strong lines, where scattering sees a slightly aspherical distribution of gas that differs from the continuum-forming region. The equatorial to polar contrast in this environment remains modest because electron scattering and line opacity dominate over bound hydrogen processes. Yet the cumulative effect is enough to bias mass flux by a small amount with latitude, and to nudge the wind into a form that is nearly spherical in bulk but marked by persistent azimuthal asymmetries. The question of magnetic fields arises naturally in the search for an organizing agent, and measurements towards stars of this class frequently return only upper limits for large-scale ordered fields, implying that if magnetism plays a role, it likely does so as a tangled small-scale component carried by the flow rather than as a strong dipolar framework that channels gas into rigid streams. A weak tangled field can still influence microphysics by suppressing heat conduction across thin layers, by guiding charged particles along shear interfaces, and by shaping the smallest scales of turbulence, where clumps rub past one another while leaving the overall dynamics governed by radiation and inertia. In the case of a strong-ordered field, one would expect clear signatures such as strictly periodic hard high-energy emission from magnetically confined wind shocks and stable phase locked modulation of lines formed near the Alfvén radius. In the observed behavior of extremely hot oxygen, rich winds, the signals lean toward irregular or multi-period variations of small amplitude, rather than toward the crisp periodicity typical of strong confinement, a pattern consistent with weak or tangled fields and with rotation-driven wind structure. Instabilities that grow in the accelerating outflow contribute a second layer of variability that does not require rotation to organize it. Line driving creates deshadowing feedback that amplifies tiny perturbations into clumps and thin shocks, and these features merge and disperse as they ride outward, adding flicker on timescales tied to the flow time from the continuum depths to the line-forming zones. In spectra, this flicker appears as subtle changes in equivalent width and wing shape across broad oxygen and carbon emission, while in high-energy bands it shows as slight short-term steps in flux, where small shocks heat pockets of gas to several million degrees Kelvin before the patches cool and mix. The interface where the wind meets the ambient interior adds still another source of change, because shear waves and cloud passages modulate mixing and produce mottled high-energy emission that drifts around the star with the lateral flow. This modulation is not strictly periodic, yet can echo the rotation if the co-rotating structures feed the interface at preferred longitudes. In polarimetric monitoring, the continuum baseline set by electron scattering wobbles, by tiny amounts when clumps cross the face, and when spiral density enhancements rotate. And across strong lines, the polarization dips and peaks move in phase, with the spectroscopic signatures strengthening the interpretation that the wind hosts persistent rotating asymmetries layered on a background of stochastic texture. The amplitude of the variations rarely exceeds a few parts in 100 for light and for line strength. In such heavily ionized sources, a level expected when the driver is a combination of mild latitude contrast, modest equatorial density bias and clumping that averages out over many zones along the line of sight. Rotation also shapes the distribution of angular momentum carried away by the wind, and although the mass loss removes spin only gradually, the tendency is to transfer more angular momentum from equatorial latitudes where the lever arm is larger. a process that can smooth differential rotation in the outer envelope over long times, while leaving the present-day wind kinematics nearly unchanged. In velocity space, the clearest rotational traces are discrete absorption components that drift from small to large blue shift in resonance lines, often appearing in sequences that repeat after several days or less, depending on the period, and their apparent acceleration matches the expected climb of speed, with radius in the outflow, when the features are tied to azimuthal structures that corrotate and then feed material along radial streamlines. When the inclination places the rotation axis near the line of sight, the signatures weaken because the azimuthal pattern projects poorly, and in that geometry, photometric and polarimetric changes become especially subtle. So inference relies on stacked observations and on cross-correlation of many weak signals rather than on a single strong tracer. Magnetic searches based on circular polarization across spectral lines often return null detections at the level of a few tens of Gauss when averaged over the visible hemisphere, and such constraints still allow stronger small-scale fields in clumps and shear layers that cancel in the meaner situation compatible with the observed microturbulent widths and with the fine filigree seen in line profile variability. In high-energy light, the presence of rotation link structure can be hinted at by a gentle phase dependence in the soft band. If one or two preferred azimuths host slightly stronger embedded shocks, yet the signal competes with stochastic variations from clump collisions, and the result is a pattern of low coherence that demands long campaigns to separate. Theoretical descriptions of this regime treat rotation, radiation, and instability together, showing that a small surface brightness wave or a tiny latitude-dependent change in line force concedes spiral density enhancements that survive many turns while being shredded at their edges into a spray of clumps, and that the combined field of these structures yields the observed mix of quasi-periodic and flickering behavior. In the deepest observable layers, the photosphere proxy samples any asphericity in true absorption, and in electron scattering and limb polarization models, predict wavelength-dependent signals at the level of a few parts in 1,000 that decline toward longer wavelengths, where the formation radius lies deeper and the geometry is more spherical. Measurements towards sources of this type are broadly consistent with such expectations when corrected for interstellar polarization. The role of rotation in shaping the termination shock is indirect but present, because the co-rotating streams deliver slightly different momentum fluxes, with longitude corrugating the shock by small amounts, and steering the lateral rivers of mixed gas along the contact surface into preferred sectors, effects that are more visible in high-energy maps than in optical spectra. On multi-year baselines, the overall pattern of variability remains steady in gross amplitude, even as details drift, suggesting that rotation supplies a clock while the wind's intrinsic instability and the ambient interface supply a source of randomization that decorrelates the fine structure. The blend gives a stable envelope of behavior within which small features wander. Uncertainties remain regarding the exact field strength on the smaller scales, the depth at which surface brightness patterns are anchored in an atmosphere without a sharp solid surface, and the degree to which rotation alters ionization, balance with latitude in a hydrogen-poor mix, and these uncertainties frame the range of models that match the weak persistent rotation, linked signals recorded across lines and continua. The observational picture, built from long high-cadence runs in light polarization and spectroscopy, supports a star whose rotation is neither negligible nor extreme, whose magnetic field is weak or tangled rather than globally ordered, and whose wind is textured by intrinsic instability, while being gently organized into co-rotating streams that repeat and modulate the spectrum and flux by small measurable amounts without overwhelming the near spherical character of the outflow, the present influence of the star on its surroundings appears as a combination of intense radiation, fast mass loss, and high-energy interfaces that together set local conditions in the cluster cavity, and these conditions register across wavelengths as brightness patterns, line ratios, and pressure contrasts that mark where gas and dust respond most directly. The luminosity supplies a hard, ultraviolet field that raises ionization well beyond the levels produced by typical O-type neighbors, so thin skins on nearby clumps brighten in lines from highly ionized oxygen and carbon and show surface temperatures of tens of thousands of degrees Kelvin, while the interiors of those clumps remain cooler and shielded, producing a layered structure at arcsecond to arcminute scales depending on distance. The mass loss injects momentum and processed material into the cavity, and the momentum flux maintains a termination shock whose pressure matches the ambient cluster interior. Around that contact conduction and mixing draw ribbons of intermediate temperature gas that shine in ultraviolet transitions, and those ribbons outline the regions where the wind shares energy and matter with the surroundings. Dust near the star is scarce because the hard field charges small grains to high potentials and sputters or sublimates them, so mid-infrared maps present faint patchy rims instead of bright continuous shells. Farther out, where density rises and radiation softens, dust survives and glows in narrow arcs that face inward, indicating where the star's photons reach with enough power to heat grain mantles without destroying them. The net ionized volume around the star blends into the broader interior maintained by the cluster, yet the spectral hardness from this source increases the fraction of higher ionization stages and alters cooling pathways, so diagnostic ratios at fixed electron density tilt toward lines that require harder photons, and this tilt persists over the thin skins of many nearby clumps. In X-rays, the shocked windsheath contributes a soft, low surface brightness, glow-mottled by small enhancements, where cloud ablation thickens the mixed layer, and these enhancements drift laterally with the flow along the contact marking, where the interface redistributes energy around the star rather than pointing strictly outward. The mechanical effect of the wind adds to the shared superbubble pressure and keeps local shell segments gently expanding. Velocities of a few kilometers per second at the rims nearest the star remain consistent with a cavity supported by a mixture of hot gas and radiation, and small differences in expansion rate appear where external density changes over short angles. The chemical signature of the outflow enriches the mixed interface with carbon and oxygen, raising the mean metal content locally and improving the efficiency of line cooling in the intermediate temperature gas. As a result, ultraviolet filaments radiate more strongly near the rivers of mixed material downstream from the star than in sectors dominated by less processed winds. In optical bands, broad emission from the outer atmosphere overlays the integrated cluster spectrum, and once separated provides a clean tracer of the star's current mass loss and ionization conditions. Nearby nebulosity exhibits weak narrow components at small velocities that ride atop that broad glow where thin skins intercept part of the field and scatter a fraction of line photons. Polarization mapping at optical and near-infrared wavelengths shows low values near the star's location and higher values along the outer arcs consistent with the dust-poor inner zone and dust-rich rims beyond. The plane of polarization aligns with the broader magnetic pattern that drapes the cavity, and slight rotations across strong stellar lines reveal the difference in geometry between the continuum-forming region and the more extended line-forming shells. The pressure gradient from the hot sheath into the cluster interior drives lateral flows that skirt the contact surface, and where those slow rivers meet, they make junctions that appear as small brightness knots in ultraviolet maps. These knots sit at locations set by the ambient pressure field, rather than by radial distance alone, showing that redistribution, not only radial expansion, sets the local pattern. In radio lines from atomic hydrogen, the cavity remains a pale basin, while in carbon monoxide the closest features lie displaced, indicating that molecular gas keeps to denser walls, and that the star influences it mostly through illuminated faces and thin evaporative flows, rather than through deep penetration. The present-day field of higher ionization also changes the chemistry of photodissociation boundaries around nearby clouds. Carbon shifts towards singly ionized form over slightly thicker layers. Oxygen remains largely atomic near the faces, and small hydrocarbons fluoresce more efficiently, brightening mid-infrared bands that trace complex carbon-rich molecules at the illuminated edges. The star's rotation-linked structures imprint weak repeating modulations on resonance lines seen against the continuum, and those modulations propagate into the nearest skins as tiny phase-dependent changes in surface brightness that are measurable only with careful stacked imaging. The pattern indicates that co-rotating streams persist to radii where clump skins respond, linking stellar variability to faint localized ripples in the surrounding glow. At the scale of the superbubble, the star acts as one of the dominant hard photon sources, keeping a portion of the interior at higher ionization and temperature than would be set by cooler hot stars alone. The effect emerges as slightly elevated electron temperatures in low-density gas, sampled by auroral to nebular line ratios, and it confines to sectors that subtend clear sightlines from the star through gaps in dust. The wind currently populates the interior with clumps and interclump plasma, moving at many thousands of kilometers per second before they are shocked and slowed. In the process, microshocks within the wind create soft X-ray photons that partly leak into the interior and brighten the contact by photoionization of intermediate ions, adding a secondary illumination that rides atop the stellar continuum. The ionization parameter immediately around the star remains high enough that oxygen reaches high stages, and carbon attains triply and quadruply, ionized states even at moderate radii, so line cooling emphasizes those ions, and the emergent spectrum of nearby skins carries the fingerprints of a very hard field at small distances that blend into a mix from several hot sources farther away. The present alignment of cluster winds sets a region of reduced external pressure on one side, where the superbubble opens toward a larger void. In that direction, the star's termination shock lies slightly farther out, and the sheath thins, while on the opposite side it sits closer in and mixes more strongly a pattern reflected in the crescent-like distribution of soft X-ray brightness and in the asymmetric width of ultraviolet filaments. In high dispersion spectra, the broad stellar lines remain stable in their extreme widths, while weak narrow features tied to external skins shift with local flows at tens of kilometers per second, tracing the gentle drift of illuminated clumps through the interior. The stability of the broad base against which these lines sit marks a steady mass loss on the timescales probed by repeated observations. The continuum measured across optical and ultraviolet bands once corrected for reddening matches an extremely high effective temperature and supplies the photon bath that maintains the observed ionization pattern locally. At longer wavelengths, free emission from the wind adds a shallow rise, and the slope indicates the density distribution in the outflow near the continuum-forming depths. The immediate thermal map thus shows a hot sheath around the star, a wind plateau of tens of thousands of degrees Kelvin that fills the outer atmosphere and thin, cooler skins on nearby clumps, where the field has softened and where recombination proceeds more efficiently, and the juxtaposition of these zones sets the texture of emission and absorption currently recorded. Across the cluster, face small arcs and pillars at the edges of denser walls present illuminated profiles that curve toward the star, and their surface brightness drops with angle away from the direct line, producing a soft, radial shading that, when combined with similar shading from neighbouring hot stars, yields a quilt of overlapping gradients whose relative weights reveal which sources dominate each patch. In sum totals measured over the inner cavity, the star's present luminosity and mass loss contribute a significant fraction of the hard ionizing budget and of the momentum input among the hottest members, and this contribution maintains high ionization in clear sectors, strengthens ultraviolet cooling in mixed layers through enhanced metal content, and keeps a portion of the superbubble interior pressurized and warm enough to support the surrounding shells at their current slow expansion rates without requiring a separate dense local bubble to exist around the star.